In this lesson, you are going to learn how to solve a rational equation. So a rational equation is where you have a polynomial in both the numerator and denominator. So what you want to do is get this in standard form equal to 0. You're going to determine the least common denominator, meaning you're going to simplify it and rewrite it in this form, where it's one polynomial over another. So you can't have like addition and subtraction, and it has to be equal to 0. And then you get to totally ignore the denominator because your x-intercepts, which is what you're really finding here, are going to come from setting f of x equal to 0. You could even think of that as, to get g of x out of the denominator, if you multiply both sides by it, you're really just left with the numerator. So in essence, you get to ignore the denominator. So you'll solve f of x equal to 0 using whatever method you need to, and then finally you're going to check for extraneous roots. Let's illustrate that with an example. Let's start with a fairly simple one. This is already in the form of one polynomial over another. There's no need to find a common denominator. So what we're going to do is we're going to set just our numerator equal to 0, which is 3x minus 2. And we're going to solve this. Well, that's pretty easy. It's simply linear. Add 2 to both sides and divide by 3 produces x equals 2/3. Now, what may not seem like a necessary step, but always is to check your solution to make sure that it satisfies the original equation. And when I do that, I get 0 over 4/9 minus 9, which would indeed equal 0. So this does satisfy my original equation. There is one solution, it's 2/3. My next equation is not yet in the form of one polynomial over another, so I need to combine and simplify my left side. In order to do this, I need to identify my least common denominator. It would be 9x. So I'm going to rewrite the left side by multiplying the first part of the expression by x over x and the second by 9 over 9. This produces x squared in the first minus 9 in the second over my common denominator, which is 9x, and this is equal to 0. Okay, so now it's in the form of one polynomial over another, so I'm going to take my numerator and set it equal to 0. This produces x squared minus 9 equals 0. It's quadratic, so I'm going to think about, well, how can I solve that? There's a couple of ways. I'm going to choose to factor. I'm going to make this x plus 3 times x minus 3. It's the difference of two squares pattern. Now I apply the zero product property, which says x plus 3 equals 0, or x minus 3 equals 0, and I will solve both of these. This produces two solutions, x equals 3, or x equals positive 3. Before I am convinced that I'm finished, I need to check my solutions. I'm going to shrink this and give myself a little more space, and I'm going to check negative 3 first. So I will do negative 3 over 9 minus 1 over negative 3, and I'm checking, does that equal 0? And this would reduce to negative 1/3 plus positive 1/3. Yep, that equals 0. So negative 3 is a solution. I'm going to check positive 3. So this would be 3 over 9 minus 1 over 3. Does that equal 0? Well, that would produce 1/3 minus 1/3, and that satisfies. So my two solutions are x equals negative 3 and x equals positive 3. Let's do another example. So in this particular example, this time we have a value on the right side. So I know I'm going to have to bring that over to the left, and I'm also going to need to create a common denominator. So I'm going to have x plus 1 over 3 minus 9 over x plus 4, and I'm going to subtract 1 equal to 0, and now I'm going to consider my least common denominator. So of course this would be the same as 1 over 1. So looking for my common factors, I have 3, x plus 4, and 1. So my least common denominator is going to be 3 times x plus 4. So I'm going to rewrite my three expressions on the left using the common denominator of 3 times x plus 4. So that means I'm going to need to multiply the first expression by x plus 4 over x plus 4. The second expression will need to be multiplied by 3 over 3. And the third expression will need to be multiplied by the entire common denominator. So I'm just going to give myself a little more space. I'm going to erase the equal 0 and squeeze in times 3 times x plus 4 on the top times 3 times x plus 4 on the bottom. Okay, now looking back here, so now I need to do x plus 4 times x plus 1. So I'm going to be multiplying two binomials together. I have 4 multiplications to make. So that will be x squared. I'm going to have plus 1x, and then plus 4x would be plus 5x for my middle terms, and plus 4. So that trinomial is produced. Next, I have a negative 9 times 3 would be minus 27. I'll switch to blue just so you can see that that came from this right here. And then lastly, here I'll switch to red. We're going to do negative 1 times 3 would be negative 3, and then I'm going to distribute negative 3. So negative 3 times x would be negative 3x. Negative 3 times 4 would be negative 12. Now I'm going to combine all of my like terms in the numerator, which would be x squared plus 2x minus 35. All over that denominator of 3 times x plus 4 equal to 0. Okay, now it's in the form of one polynomial over another, so my solutions or x-intercepts are going to come from the numerator. Now I have a quadratic equation, so I could do the quadratic formula, or I could attempt to factor this. I always attempt to factor first, I just am quicker at it. So factors of negative 35 that add to 2. So let's see, that's going to be a positive 7 and a negative 5. Now I'm going to apply the zero product property, which says each factor, x plus 7 equals 0, or x minus 5 equals 0. So my two solutions would be x equals negative 7 or x equals 5. You'll sometimes see your solution set written like this. But before I officially do this, I'd better check for any extraneous roots. Solutions that look like they are solutions, but when you plug them back into the original, they don't satisfy the equation. So to do that, I'm replacing all of my x's with my potential solutions. So in the first, I'd have 5 plus 1, which is 6, and 6 over 3 is 2. Minus, I'd have 9 over 9, which is 1. Does that equal 1? That does indeed. I'm going to check the other one. So this time I'm substituting negative 7 in and checking if my left side equals the right. So negative 7 plus 1 would be negative 6. Divided by 3 would be negative 2. Minus, let's see, in the denominator I would have negative 3. 9 divided by negative 3 would be negative 3. So I'm going to have negative 2 minus negative 3, which is the same as 2 plus 3. So this works. Neither solution is extraneous. In this last example, we are actually given a rational function, okay? But on the right side, I notice that I don't have this expression written as one polynomial over another. So in order to do that, I'm going to need to use my skills to find a common denominator before I start analyzing this function. So I'm going to factor my first, or this middle denominator, and I recognize that as the difference of squares pattern. It's x minus 5 times x plus 5. So that's telling me that my least common denominator is x plus 5 times x minus 5. So I'm going to rewrite this expression so that I can find a common denominator. So the first part of the expression needs to be multiplied by x minus 5 for x minus 5. This middle portion already has the common denominator. This last one needs to be multiplied by x plus 5 over x plus 5. So now I can rewrite all of this, let's see, with the common denominator. And I'm going to distribute the 2, which gives me 2x minus 10. I can just recopy the plus 20 in the middle. And now I'm going to distribute the negative 3. So negative 3x minus 15. And I need to combine my like terms, which looks like I get negative x. Negative 10 plus 20 would be 10, and then 10 minus 15 would be negative 5. And this is over x plus 5. It's x minus 5. And in order to graph this polynomial function and analyze it, I want to see if I can simplify this any further. So I recognize that in the numerator, that if I try to factor this at all, it has a common factor of negative 1. So I'm going to pull this negative 1 out, and that would make it x plus 5 on the top. Why would I do that? Well, that's going to help me determine any holes that exist where I would have removable discontinuity. So x plus 5s would cancel, and this function simplifies to negative 1 over x minus 5. So I know that I have a hole at negative 5 because the factor is x plus 5. And if I wanted to get the y value of that hole, I would plug it in to the simplified function, and that would give me negative 1 over negative 10, or 1/10. The reason you would want that y value is because it's going to help you determine any breaks in your range. Okay, that means I have removable discontinuity. And let's talk about any asymptotes. So I do have a break in my denominator, so it'd be a break in the domain. So I have infinite discontinuity at a vertical asymptote. Infinite discontinuity, and that comes from the factor in the denominator that remains, the x minus 5. So that would be removable infinite discontinuity, and it would be at x equals 5. I'm going to think about any horizontal asymptotes now. And I would have a horizontal asymptote because the degree in the denominator is greater than the numerator. So it would be y equals 0, which would affect my end behavior. It would be approaching 0 on both the left and the right. So the limit of f of x as x approaches both negative and positive infinity would be equal to 0. All right, so I also need my x and my y-intercept. So the y-intercept would be found by doing f of 0. So if I plug in 0, I would get positive 1/5. So my ordered pair would be 0, 1/5. And my x-intercepts would come from solving the equation where I set the numerator equal to 0. So the numerator is negative 1 equals 0, and that's nonsensical. And why would that be? Well, we already kind of saw that we have a horizontal asymptote at 0, so very rarely will your curve pass over a horizontal asymptote. There are some exceptions to that, but our x-intercept then does not exist. So to do a sketch here, I know that I have a vertical asymptote at 5. At x equals 5. I have a horizontal asymptote along the x-axis at y equals 0. It crosses, or the function crosses, the y-axis at 0, 1/5. So like right here, and I have a hole at negative 5, 1/10. So it's really, really close to the y-axis, and I'm just going to erase my notation here so I can emphasize a hole at negative 5, 1/10, and that's too big. But now if I just kind of look at my calculator screen, I'm going to see infinite discontinuity. I'm emphasizing my horizontal asymptote, and approaches both asymptotes. And because it's great practice, let's just state the domain and range as well. So my domain would be from negative infinity to negative 5, where I have that first hole, union negative 5 to 5, where I have the asymptote, union 5 to infinity. Now the range, how low, would go from negative infinity up to my horizontal asymptote of 0, union 0 to, now not positive infinity because I do that hole, which is why it's helpful to have this y value of the hole where it exists. So 1/10 union 1/10 to positive infinity.